Hi guys, today we're going to be running through 8.040, the blue sheet that you got yesterday, and this is going to be on concentration cells. So yesterday we talked about galvanic cells, which again is kind of like a glorified battery. You've got our redox reaction, we separate it into its two halves, and there's a potential between those two half reactions that allows this transfer of electrons to occur through our wire. So today, concentration cells is pretty much the exact same thing, but instead of being under standard conditions, which represent 1 molar concentrations of solution, we're going to be changing that a little bit and see how that affects our cell. So up top, we've got a little review. You see Gibbs free energy standard, enthalpy standard, entropy standard, and energy standard. And that little degree symbol, of course, means that we have 1.0 molar, 1 atmosphere of pressure if we're talking about gases, and 298 Kelvin. Okay? So, the next example of our redox reaction right below, we can figure out just like we were kind of doing yesterday. So we have an oxidation half, a reduction half. In this example, we've got copper metal on the left-hand reactant side, and that's going to turn into copper 2+ ions. Again, whenever you have a metal, solid metal, okay, more often than not, that's going to be oxidized. So that's going to be our oxidation half reaction, is our copper going to copper 2+. If you wanted to do it like we were doing it previously, that's just fine. We can set up all of those oxidation numbers and take a peek at that as well. Copper 0, cerium 4+ is 4+, copper 2+ is 2+, and cerium 3+ is 3+. So we've got an oxidation occurring between the copper metal over to the copper ions. We've got a reduction occurring between the cerium 4+ and the cerium 3+. Okay? So let's balance this thing out. We've got copper solid changing into copper 2+ aqueous. Okay? To balance that half reaction, the charges, we need to make them work out, so we've got to add 2 electrons on the product side. Okay? For the reduction half reaction, we have 2 cerium 4+ aqueous. On the reactant side, we have 2 cerium 3+ on the product side. And we got to again balance out charges. That's going to require 2 electrons on the reactant side. Okay? So we can look these up. Okay? The first one, the copper reaction, we've seen a whole bunch. That's on the back of your periodic table. But the second one's actually not on your periodic table. So this is a good opportunity. If you have not looked at the appendix in the book or used the book for these reduction potentials, the book has a whole heck of a lot more than your periodic table does. You can find this either in Chapter 18 or in the very back of the book in Appendix 25. Either place is fine. They're the exact same table. Okay? So the copper one, we looked that up. That's oxidation, so we've got to flip it, and we end up getting a negative 0.34 volts. For the copper one, for the cerium one, the reduction of cerium 4 to 3, we have a positive 1.7 volts, and that's going to give us an E cell, a standard cell potential for this reaction of 1.36. Okay, so if you're determining the standard cell potential, what is the concentration of each species? Kind of like what I said up top, right? If you have a standard conditions, we're talking about 1 molar solutions. Okay? According to Le Chatelier's principle, what would happen if we increase the concentration of cerium 4+? So don't overthink this. Just do it like we would at an equilibrium unit, right? If we increase the concentration of the cerium 4+ on the reactant side, which way are we going to shift? Well, we're increasing something on the left-hand side. We're going to shift away from that to reach equilibrium. So we're going to shift right. Okay? And what's going to happen to our new value of the cell potential? Okay? If you notice the difference between this and this, the only thing different is that little degree symbol. The degree symbol implies standard, which means 1 molar. The one without it implies some other point in time. So in this case, we've increased the cerium 4+ ion. We've shifted to the right, making this more favorable, right? We're moving towards products. So in other words, our value of E cell is actually going to be larger. We've made this a more favorable process. And remember, when the cell potential is positive, it's spontaneous. So if we've pushed it further toward the products, we've made it more spontaneous, so to speak, and the value is going to become more positive. So we have this relationship between our original conditions and our new conditions. Okay? So this is what a concentration cell is. You've got some difference in molarity as opposed to just the standard 1 molar. And it really turns into a Le Chatelier question. You increase something, you decrease something. Which way does that push your redox reaction? Which way does it shift? And then how does that value or that shift change your value of the potential? Okay? So let's do this again. We can try a similar problem. If we were to change the concentration of the copper 2+, the cerium 4+ is 1 molar, the cerium 3+ is 1 molar. Those are the same as standard. Okay? But copper 2+ we've now increased. If we go back to the original reaction, copper 2+ is a product. If that goes up, again, we're going to have to shift to the left. Okay? Okay, we're going to shift away from that increase. So now if we're shifting left, our new value of the potential, after we've increased that concentration, okay, is going to have to be smaller. Because again, the forward direction, or moving towards products, is the favorable or the spontaneous direction. So if we're moving in the opposite direction, our new value of E cell, not at standard conditions, must have had to have become more negative or gotten smaller. Okay, let's keep going. In this picture of a galvanic cell, if you take a look at both sides, what you'll see is that we have 2 silver electrodes and 2 solutions that are each 1 molar silver 1 ions. Okay, and the question here is which way will our electrons flow? Okay, but if there's no difference in either side, what we're really trying to do is we're really trying to oxidize silver and reduce silver ions, but that's the exact same reaction, just in reverse. Okay, so the reduction is already written for you. I'm going to write the oxidation right above that. Okay, and the oxidation potential of that reaction is going to be the opposite of the reduction potential right below it. So this is going to equal negative 0.8 volts. So the total cell potential of this reaction is going to end up being 0. And that's the very final question here. So it's nothing. Okay, what does that really mean? That means that this reaction isn't favored in either direction. It's at equilibrium. Okay, so which way will the electrons flow? Well, they won't. Okay, and explain our thoughts. Well, the thought here is that if there's not a difference, or the potential of the reduction and the oxidation are equal and opposite, we're at equilibrium. Okay, so let's flip the script a little bit. Let's change our setup and mess with one of those concentrations. Okay, same materials in this example. The only difference is that we've now taken the 1 molar solution on the right and we've reduced it to 0.1 molar. So now, on the surface, this might look kind of similar, right? We've got silver electrode on both sides, silver ions on both sides, but that difference in concentration is going to make this actually a usable galvanic cell. So the question here is which way will the electrons flow in this galvanic cell again? And then the next little block of words will probably hopefully help you answer that question. So the cell wants to equalize its concentrations. Okay? So silver ions in the left cell will need to decrease, while the silver ions in the right cell will need to increase. Okay? So if we want to remove ions in the left cell, what we really want to do is we want to reduce the Ag1+ into silver metal. So the reduction is going to occur on the left-hand side. And the oxidation is going to occur on the right-hand side. Okay? So the question of where the electrons are going to flow is going to be based upon the negative and the positive side, the anode and the cathode, Okay? And this is actually the exact reverse of what we've normally drawn so far in this unit. Our electrons are going to flow right to left. Okay? The right-hand side is now going to be your anode. The left-hand side is now going to be your cathode. And again, oxidation occurs at the anode, reduction occurs at the cathode. You can remember that with the vowel, and consonant combination. Okay? The very last question says, what factor contributes to our overall cell potential? And essentially, it just has to do with the fact that we have different concentrations. Okay? Because our concentrations aren't equal, we get this difference. All right? Remember, when you have the value of the reduction potential that you look up, that's always at standard conditions. That's always talking about a 1 molar concentration. So if we mess with the molarity, that value you look up in the back of the book is no longer what you think it is. We're no longer under standard conditions. So the left-hand side here, which we're reducing, is going to be a positive 0.8 volts. But the right-hand side, because of that difference in concentration, is now something different. It's something less. Okay? So our overall E cell no longer equals 0. There's going to be a difference, and this is going to flow in the direction that makes our concentrations end up being equivalent once we reach equilibrium. All right, a little bit of review for labels here. We've got all sorts of different kind of funky variables coming in this unit. So the first one there is the cell potential. The units of cell potential are volts. Okay? Or if you want to break that apart, we can say that it is joules per coulomb. Okay? Delta G gives free energy from the previous unit. That was always given to us in joules or kilojoules. Doesn't really matter. I'm just going to put joules. Okay? Faraday's constant is that the next stylized F. The units of Faraday's constant are coulombs per mole of electron. Okay. Little n means moles, but in this unit, because we're dealing with the transfer of electrons, more specifically, we're talking about moles of electrons. Okay. R is the gas law constant. We're going to use that again for just a little bit, and because all of our other units are in joules, our value of the gas law constant R is also going to be used in joules. So we're going to use this version. And last but not least is temp. Temp we're always going to use in Kelvin. Okay, so just a little refresher on what those units are going to be for those various things that we're using. All right, to the back. The first one on the back gives us a line notation. This was from yesterday as well. Hopefully you can remember how that setup looks. On the very far left-hand side, you have your anode. On the very far right-hand side, you have your cathode. Okay. And then in the middle, these two double lines represent your salt bridge, or the separation between your two sides of the cell. Okay, so this is your salt bridge in the middle. Okay? So, if we have a concentration of aluminum 3 plus equal to 0.4 molar instead of the 1 molar up above, will our new value of the cell potential be greater than, less than, or equal to the original standard cell potential? Okay, so again, in reality, this is talking about a Le Chatelier problem, a Le Chatelier's principle problem. We're going to change the concentration of one of our reactants or products. Which way does it shift, and how does that affect the value of the potential for this reaction? Okay. Now, what's kind of tricky is with line notation, you have to be very, very careful. The double line in the middle, the salt bridge, is not an arrow. The reactants are not aluminum and aluminum 3 plus, and the products are not lead 2 plus and lead. We have to look at each of those sides individually. So our reactants in this reaction are actually going to be the aluminum solid plus the lead 2 plus ions, and that's going to produce our aluminum 3 plus and our solid lead. Okay, this is not balanced, but we can do it pretty quickly. This is a redox reaction. If we really wanted to do it appropriately, we'd break it in half, do an oxidation half, a reduction half. But at the end of the day, we can kind of just look at the charges and make some quick math of it. So we've got positive 2 on the left, positive 3 on the right. If we triple the lead and double the aluminum, we're going to have a balanced reaction. So I'm going to do that. Okay. So here's the question again. Let's go back to what I was asking. We've lowered the concentration of aluminum. Okay, so the concentration of aluminum 3+ has gone down. That's a product in our redox reaction. So we've removed some of the product. The shift is going to be to the right to replace that. So what we've really done is we've made this thing more spontaneous. Okay, we've pushed it further towards the product side. So our new value of the cell potential is going to be larger than the original value of the standard cell potential. Alright, this is from the book. I figured it's a good thing to read, and it kind of reiterates what I was talking about up above when we looked at the cell that was equal concentrations of silver ions and silver ions on both sides. So a dead battery is one in which the cell reaction has reached equilibrium, and there is no longer any chemical driving force to push electrons through the wire. In other words, at equilibrium, the components in the two cell compartments have the same free energy, and delta G equals 0 for the cell reaction at the equilibrium concentrations. The cell no longer has the ability to do work. So again, all these batteries are going to reach a point where either you run out of reactants, okay, or you get to a point where equilibrium is simply reached, and this thing can't possibly do any more work. There's no longer a difference in potential for your two half reactions. Alright, let's do this. So, we have some chromium ions, we have S4O6 2- ions, and this is a redox reaction that involves all aqueous species. We haven't really seen that before. We've been dealing with a lot of solids and metals as our electrodes, and we don't have to worry about setting up the cell in this example. We're just going to look at the reaction. But the first question here is asking us, what's the delta G? What's the Gibbs free energy for this system? Okay, and this is where we're going to bust out our new equation that we kind of looked at just really quickly at the end of class yesterday. So the new equation we're going to use is this. Okay, that's in your formula packet, so hopefully you can reference that whenever you need it. And let's refresh what each of those variables means. Little n is the number of moles of electrons that are transferred in our process. F is Faraday's constant. And E cell, is the potential of the reaction we're looking at. So we already have E cell from up above. We see that that is a positive 0.67 volts. Faraday's constant we can simply look up. That's 96,485 coulombs per mole of electron. And then the moles of electrons transferred we might have to think about just a little bit, but we can look at that. So let's take a quick glance at our half reaction here. I'm going to use chromium because that looks a little more friendly. So let's look at the chromium process here. We have chromium 2+ going into chromium 3+. And we need to balance this out with some electrons. And it looks like we have a factor of 2 from the original reaction, so let's make that a factor of 2. We need to add 2 electrons on this side. Okay? And that's our N. That right there is the value of N. How many moles of electrons are we moving? Being lost in the oxidation and being gained in the reduction. Okay, so we've got everything we need. We just got to kind of plug and chug. So delta G is going to equal a negative value of our 2 moles of electrons multiplied by Faraday's constant, which is 96485 coulombs per mole of electron, multiplied by the potential of our cell, which is 0.67 volts. I'm going to write volts as joules per coulomb, and you'll see why in a second. Okay, so we plug all that in. Moles of electrons cancels. Coulombs cancels. And we're left with a value of delta G that's just simply going to be equal to joules, which again makes sense. Our value of Gibbs free energy should always be in joules or kilojoules. Okay? If you plugged all that in, you're going to get a value of delta G equal to negative 1.3 times 10 to the 5th joules. Okay? And then the question is this favorable? Yes, it is. Negative Gibbs equals a favorable reaction. Of course, we could have answered that right away, because with a positive cell potential, a positive voltage from the cell potential, that also is an indication of a spontaneous or favorable reaction. All right, let's combine our Gibbs free energy equations. The next question says, hey, calculate the equilibrium constant. Okay? That's going to bring back this value, or this equation of Gibbs free energy. All right. We're at standard conditions, so we know our temperature is 298. R is simply going to be the gas law constant in terms of joules per mole times Kelvin. And then we can rearrange this, use the Gibbs free energy that we just solved for, and solve for our large value of the equilibrium constant, K. So let's plug this in. We know that delta G is negative 1.3 times 10 to the 5th joules. That's going to equal R. In terms of joules, R is going to be a 8.314 joules per mole times Kelvin. Okay. Temp is 298. Then we have natural log of K. If we rearrange that mathematically, we can solve for natural log of K equaling the rest of this numerical value. To get rid of a natural log, again, you have to take E, the mathematical constant E, to the power of both sides. And when you do all of that, you should be able to get a value of K equal to 6.1 times 10 to the 22nd. Okay. You'll have to check that on your own time, but that should be what you get. We're almost done with this sheet. Okay. The next question regarding this reaction is, what are two things, or what are two ways we could change the concentrations to make this thing less favorable? In other words, we want to shift it back towards the reactants. We want to make our value of the cell potential more negative or less than the 0.67 that we started with. Okay, well, this is Le Chatelier's again. This is simply Le Chatelier's principle. What could we possibly add or remove to make this shift left? Well, if we remove either of the reactants, that would shift us left and cause our value of the cell to go down. If we add either of the products, that would also cause our value of E cell to go down. Any of those concentration changes would push our reaction to the left, causing the spontaneity or the favorability of this reaction to go down. Last question, and this is kind of a recap of what we just did, but this is asking us, with this information, with that balanced redox reaction and the cell potential of that redox reaction, what are all of the things we could possibly solve for? Okay. The first one there is electromotive force, EMF. If you remember from the first day or earlier this week, electromotive force is cell potential. So those are one and the same. Can we solve for that? Yes, we can. Enthalpy and entropy. It's really close. It looks like we could maybe solve for one or the other, but at the end of the day, the only equation we really have to compare our Gibbs free energy with enthalpy and entropy requires that we would need to know at least one or the other. If we knew enthalpy, then we could solve for entropy, or vice versa. But we don't know either of them, so in this example, we actually can't solve for either enthalpy or entropy. Free energy, Gibbs free energy that is, we can solve for that. We just did that. Okay, we have to use the cell potential, we use the number of moles of electrons transferred, we use Faraday's constant, and we can plug all that in and get a Gibbs. The rate of reaction, that's talking about kinetic stuff. How fast is this thing occurring? That we can't do. The only way we can really understand the rate of a reaction is based upon doing an experiment and recording some values in the lab. So we don't know the rate. The thermodynamic favorability, yeah, we know that. Okay, a positive E cell or a negative Gibbs will tell us that. Spontaneity, sorry, I'll make a check mark, I suppose. Spontaneity, same exact thing, we know that. Equilibrium constant, that's big K. That's the last thing we saw for. Yep, we can do that. Pressure. This one's a little indirect, but we're under standard conditions. Meaning, our pressure is 1 atmosphere. So at first glance, it might not seem like something that we would know. It's not really relevant because we're talking about aqueous solutions, but at the end of the day, standard conditions means 1 atmosphere, so we do know our pressure. The volume, that has no bearing on this problem again. It's really the concentration, right? So we know that these are 1 molar concentrations because they have to be, because that's standard. But as far as the volume of stuff that we have, that's kind of irrelevant. So we don't know that. We really don't need to know that. And then last but not least, we have the temperature. Again, the little degree symbol, the standard symbol, tells us our temp. We're at 298 Kelvin. Okay? So with just that little bit of information, with just a balanced redox and a cell potential, we can figure out a whole bunch of stuff. And we can use our Gibbs free energy equations to kind of get in between a couple of different units. Okay? So I hope that was helpful, guys. Good luck. Work on your homework, please. Topic 2 is due tomorrow. Topic 3 will be due most likely on Thursday. I'll come back tomorrow and see how this video went for you guys and make a decision then. But I would anticipate that topic 3 is going to be due Thursday.